Dear friends, I'm Professor DG going to take your third lecture related with electromagnetics. This is in a paper PH 6503 and this is our third lecture. The first lecture was related with the Maxwell's equations and using that Maxwell's equation we can describe the electric field and magnetic field and the surrounding space. So to describe that one, you have to solve the Maxwell's equations and solving the four Maxwell's equation is little difficult. So compared to that, if the number of equations was reduced to two, that is called electromagnetic potential. So we have defined the electromagnetic potential in a both the conditions, that is the static conditions, that is a scalar potential phi and a vector potential A. From scalar potential phi, negative gradient of potential will give the electric field and curl of vector A will give the magnetic field. And this potential was actually modified in last lecture for time varying electromagnetic fields, and that is electric field is equal to divergence of electric field is equal to minus grade phi minus del A upon del T and vector B is equal to curl of vector A. This way the magnetic field and electric field can be calculated from the scalar potential and vector potential in time varying fields. This we have studied in a last lectures. Moreover, we have also studied about the gauge transformation. That is, A is transformed to A dash, A plus del psi, and phi was transferred to phi dash, where phi dash is equal to phi minus del psi upon del t. This way, this is called a gauge transformation that we have studied, and we have seen that the electric field and magnetic field is not going to be changed by modifying this gauge transformation. A to A dash and phi to phi dash, electric field and magnetic field remains invariant. We have solved all the four Maxwell's equations and we have obtained identical equations. And to obtaining that identical equation, we have choose that time the Lorenz gauge conditions. What was the Lorenz gauge conditions? The relations between the scalar potential and vector potential. That is, divergence of vector A is equal to minus mu0 epsilon 0 del phi upon del t. This is the Lorenz gauge conditions, which is we have choose at that time arbitrarily. But actually it is not arbitrarily. It can be derived, and it was derived by Mr. Lorenz, and that we are going to study over here. These Lorenz gauge conditions is for the dynamic fields. That means fields are function of r and t, position vector as well as time in that case. If the electrostatic field is to be there, then divergence of A is equal to 0 was considered, and that was known as a Coulomb gauge condition. So now we are going to derive the Lorenz gauge condition here. That is the topic 5.11 from BB Lab. More about the Lorenz gauge conditions. The Lorenz gauge condition is not quite an arbitrary as it appears at the first sight. So we have choose in a previous section the Lorenz gauge condition arbitrarily because we wanted to obtain the identical equation for vector potential as well as for the scalar potential. But now what we are going to learn here that whatever the Lorenz gauge condition was derived by him, which can be derived from the first principle of electromagnetic theory. Which are the first principle of electromagnetic theory? For electrostatic field, it is starting from the Coulomb's law, and magnetostatic field, which is starting from Biot-Savart law. So Coulomb's law and Biot-Savart law and principle of conservation of energy, that is equation of continuity, divergence of J is equal to minus del rho upon del T. These are nothing but you can say that first principle of electromagnetic theory. So now we are going to utilize the first principle of electromagnetic theory sorry, which was actually utilized by Mr. Lorenz. We are studying here, and this Lorenz gauge condition is derived from this. So while deriving the Ampere circuit law from Biot-Savart law for stationary current distribution, the Coulomb gauge condition divergence of A is equal to 0 appears in a natural way. So when Amperes has derived the Ampere circuital law from Biot-Savart law, he obtained the Coulomb divergence of A is equal to 0 appears in a natural way for static conditions. That means the magnetic field and electric field is only a function of position vector, but they are not function of time. Then divergence of A is equal to 0 was derived. Now the same conditions, divergence of A is not equal to 0, but it is going to be minus mu 0 epsilon 0 del phi upon del t, that we are going to derive here for quasi-stationary condition. That means when both the fields are time depending also, that means it is a function of time also. So we are here starting from the Biot-Savart law. Consider that in our XYZ coordinate system, there are two loops. One loop in which the current is flowing. That loop is it is the source of the magnetic field, and hence we can say that loop 1 is a source loop. And because of that current which is flowing in that loop, this loop is going to be divided into a number of current elements, IDL1, IDL2, IDL3, etc., etc., and each current element will be having a position vector with respect to origin. That position vector can be definitely designated by R1 dash, R2 dash, R3, R1 dash, R1 double dash, R2 double dash, R3 double dash, like that way. Because these position vectors are related with each current element in a source loop. And because of that, the magnetic field is going to be linked with the another loop, and that another loop which is magnetic field is going to be there, which is where you can obtain at different points, which is a position vector R2 will be there on a field loops. So that is going to be the position vector R2 at some point on a loop 2, and that we can designate as A is the function of R2. That means vector potential at a position vector R2 on a field loops, that is equal to mu 0 upon 4 pi. How you can obtain? Because of the current which is moving in a loop 1, and that is going to be given by current density J, which is a function of a different position vector R1 in a source loop upon distance from position vector R1 to the position vector R2, displacement vector. So this is nothing but the modulus of R2 minus R1, that is the distance from each current element to the point R2 where you are obtaining the vector potential AR2 d tau. That is called a polymer image. So equation 5.75 is nothing but Biot-Savart law is there. So now on this Biot-Savart law, we are going to operate del 2. That is nothing but a differential operator. We are going to operate over the vector field, and hence del 2 dot AR2, because we are interested in divergence of vector A. So we are operating now del 2 over a vector A2. Here you can see that the subscript 1 and 2 refers to the source and field coordinates. Hence, del 2 dot AR2, that is equal to mu 0 upon 4 pi. Here we are operating del 2 both the sides. So on this side, GR1 is coming outside dot del 2 into 1 upon modulus of R2 minus R1. Del 2, if it is operating on a scalar quantity, then it is a gradient. So you can say that gradient del 2 of scalar quantity 1 upon R2 minus R1 d tau 2. So equation 5.75, when it is operated with del 2 both the sides, you will get equation 5.76. Here we operate del 2 on vector R2 only. Now, what is the relationship with the del 1 and del 2? When it is operating on R2, then it is going to be positive. But when del 1 is operating on R2, then it becomes negative. So, since the gradient del 2 of 1 upon R2 minus R1 modulus, that is equal to minus grade 1 upon modulus of R2 minus R1 will be there. So this value which is operating with we are replacing del 2 with del 1. So the minus sign will coming outside. So this equation 5.76 can be written as del 2 dot AR2, that is equal to mu 0 minus mu 0.45, because this minus sign is added here, minus mu 0.45 volume integration V1 of GR1 dot del 1 upon modulus of R2 minus R1 d tau. Now this is one of the equations of vector identity where del is operating on a scalar quantity phi as well as it is operating on a vector quantity vector field A. So here the product rule was applied. That means one of the quantity was taken constant and del is operating on another quantity, then another quantity was taken a constant and del is operating on the first quantity, and that way you can see that this is the equations where del 1 which is going to be operating on a vector quantity gr1, current density is the vector quantity, and scalar quantity phi is nothing but 1 upon modulus of r2 minus r1 is a scalar quantity. So del which is operating on a scalar and a vector quantity can be written as like this. The scalar quantity phi was taken constant, 1 upon modulus of r2 minus r1 is taken constant outside, and del is operating on vector quantity, that means del 1 dot gr1, and then gr1 was taken outside, that is a constant taken outside, and del 1 is operating on a scalar quantity 1 upon r2 minus r1. So this equation del 2 dot AR2 of this equation is replaced by another two terms. That means this value is substituted in this forms. That is mu 0 upon 4 pi volume integration V1 of 1 upon scalar quantity modulus of R2 minus R1 into divergence of del 1 dot GR1 d tau 1 minus volume integration of del 1 dot gr1 upon r2 minus r1 d tau 1. So this equation is replaced by these two equations. Now we'll concentrate on the second part of the equation 5.77. This is the divergence of the two forms using and volume integration is there. So we want to convert from this volume integration to the surface integration using the divergence theorem. So using the divergence theorem, the second integral can be written for a bounded source distribution. That means the current is flowing in the source loop and the surface of the source loop is the surface, total surface. So the surface integration is converted. So this divergence, using the divergence theorem, the volume integration of divergence of del 1 dot gr1 upon r2 minus r1 d tau 1, this is volume elements, that is equal to the surface integration of gr1 upon modulus of r2 minus r1 dot en caret unit vector of surface elements everywhere into ds over the entire surface which is bounding this volume where the current density J is going to be flowing. But current density doesn't come out of the surface, and hence this surface integration is going to be 0 because nothing is coming out from the surface. Electrons is not coming out of the surface of the loop 1, and hence no flux is coming out through the surface of the loop 1, and hence this integrand is going to be 0. And hence this equation 5.77 is reduced to del 2 dot AR2, that is this, is equal to only the first term mu 0 upon 4 pi the volume integration of the scalar quantity 1 upon modulus of R2 minus R1 into divergence of del 1 dot J1 d tau. So divergence of J is nothing but equation of continuity. So we can replace this one using the conservation of charge, that is equation of continuity. Divergence of J is equal to minus del rho upon del T, where rho is nothing but volume charge density at different line elements position vector which is a function of position vector r1. So del 1 dot jr1 can be replaced by minus del t of rho, which is a function of position vector r1. Now, so del 2 dot ar2, that is equal to mu 0 upon 4 pi volume integration of the scalar quantity as it is 1 upon modulus of r2 minus r1 into, we have replaced the divergence of j is converted into minus sign. Minus sign is taken outside. Del t of rho r1 d tau 1. Now, here, using the Coulomb's law, what is the potential because of the volume charge density rho inside the entire source loop? That can be given by this equation using the Coulomb's law. So, phi is the potential, electric potential, the scalar potential at a position vector r2 because of the charge density rho, which is a function of position vector r1 over the entire loop, where r1 is supposed to be the variable vector. Remember, 1 upon 4 pi epsilon 0, the volume integration of rho is a function of r1 upon this distance is also variable because r1 is variable, and this potential was obtained at position vector r2. So r2 minus r1 d tau 1. So this is the Coulomb equation, and that we are going to substitute here. Or this equation will obtain in the form of Coulombic equation. Now in this equation, you can see that this is a volume integration and this is a differentiation. So integration and differentiation both are there. So this is the integration over the space coordinate and differentiation over the time coordinate. We can interchange their order. It makes no difference, and hence del t can be taken outside. Moreover, in this equation, we are interested in mu 0 epsilon 0 or 1 upon 4 pi epsilon 0. So what we'll do here, we'll multiply and divide numerator and denominator by epsilon 0. So this quantity in denominator becomes 1 upon 4 pi epsilon 0. That we'll take inside this bracket. So the upper term is nothing but minus mu 0 epsilon 0 del t, that is the differentiation we are taking outside, that del t is outside, into inside the bracket this 4 pi which was multiplied with epsilon 0, so it becomes 1 upon 4 pi epsilon 0 volume integration of rho r1 upon modulus of distance r2 minus r1 d tau 2. So inside this bracket, whatever quantity is there, it is nothing but the potential from the Coulomb's law. So we have converted this equation 5.79 in terms of the Coulomb's equation also. So we can substitute for this Coulomb's law. That is nothing but the potential at a function of R2. So this is equal to del 2 dot AR2, that is equal to minus mu 0 epsilon 0 into del t of phi R2. And if you write in general, that is nothing but the divergence of A is equal to minus mu 0 epsilon 0 del phi upon del t. This is the vector potential, this is the scalar potential, and they are related by this equation, and this equation is known as a Lorenz gauge condition. So the Lorenz gauge conditions which we have obtained, we have choose actually in the previous section, was not chosen arbitrarily, but it was derived by Mr. Lorenz, and that is the way we can understand that it is derived from the first principle of electromagnetic theory. Now, using these Lorenz gauge conditions, we can obtain the displacement current also. How we can obtain the displacement current? Let us see here. We know that curl of factor V is equal to, we can substitute that B is equal to curl of factor E, right? So, if we want to find out the magnetic field B at a position vector R2, that is nothing but the magnetic field at a position vector R2 is equal to curl of vector potential at position vector R2. So we can replace del 2 cross BR2 is equal to del 2 cross AR2. Here this is nothing but the vector triple product A cross B cross C. That means we can expand this one using its vector triple product identity. That means middle vector comes always with the positive sign. So middle vector is del 2, is outside with the positive sign. Its coefficient is the dot product of the remaining two vectors, del 2 dot AR2. That is the coefficient of del 2 vector minus second vector with the negative sign. That means vector field AR2 is a negative sign. And dot product of the remaining two vector del 2 dot del 2, that is nothing but the Laplacian operator del square. So minus del 2 square AR2 will be there. Now we will solve first and second term individually. So first we are taking the first term del 2, that is gradient of divergence of AR2 vector field. So first term is equal to minus del 2 and del 2 dot AR2, that we can substitute from the Lorenz gauge condition. That means value of del 2 dot AR2 we can substitute in terms of minus mu 0 epsilon 0 del phi R2 upon dt in this equations. And hence the minus sign is taken here. Now, if we take mu 0 outside, and del del t is also taken outside, because this is a differentiation with respect to space coordinate, and del del t is a differentiation with respect to time coordinate. So we can change the order of differentiation. So whether we take the first differentiation with the time coordinate and then the differentiation with the space coordinate, it makes no difference. And hence we can write this equation like this: minus mu 0 is taken outside, del del t is also taken outside, and minus epsilon 0 del 2 is taken inside, which is operating on scalar potential phi R2. So negative gradient of potential is nothing but the electric field. So that we can substitute here. This is nothing but the negative gradient of potential minus del phi, that is electric field, and this is replaced by vector E. So you can see that this is equal to mu 0 del del t of epsilon 0 E, and epsilon 0 is nothing but displacement electric field vector, that is equal to mu 0 del capital D upon del t. This is equation 5.82. So for the first term in this equation, we can replace by mu 0 del D upon del T. Del D upon del T is nothing but the displacement current density. Now we'll see the second term, which is operating Laplacian operator over a vector potential. We can utilize using the Myers-Servat law. The second term, del 2 square AR2, that means del 2 square Laplacian operator is operating on a vector potential. That is equal to minus mu 0 upon 4 pi, the volume integration of JR1 del 2 square is operating on the scalar quantity modulus of R2 minus R1 d tau 2 d tau. But this is equal to mu 0 JR2, where we have used the equation 3.163. That means in chapter number 3, this quantity is already mathematically derived to this value. So this value will directly substitute here. So here in the first term is going to be, you can say that this term mu 0 del D upon del T, and the second term mu 0 J will be substituted here. So in general, we get del cross B is equal to mu 0, which is common for the both the terms, will be taken outside, J plus del D upon del T. B is equal to mu H also. So you can say that B is equal to mu 0 J H. So this is mu 0 will be cancelled. So del cross H is equal to J plus del D upon del T. We see that this statement also leads to the displacement current. So this way we can obtain the displacement current from the Lorenz gauge condition also. Thank you very much, friends.